Welcome, fellow software engineers. Welcome to the sixth lecture. Actually, there's a typo here. I think, well, hopefully there it is. I have to check if that's the. Yeah, there's. I didn't correct these dates on the first page. But it's the sixth lecture, and we're continuing on the topic of concrete syntax. So again, what is concrete syntax? Maybe recap some lectures ago. We said we want to define formal languages, and they consist of an abstract syntax, a concrete syntax, and semantics. Abstract syntax is what we have been defining by meta-modeling in the first lectures, and in the last lecture we talked about concrete syntax, that there can be graphical or textual concrete syntaxes, and what are the advantages and disadvantages of graphical versus textual syntaxes. So we had some advantages that graphical syntax is very nice if you want to visualize object relationship concepts, but it also has disadvantages. So textual syntax is much easier tooling-wise typically, and if you want to do things like diff and merge, this is usually easier with textual languages. Also, large models are hard to visualize or to maintain in a graphical editor. Then sometimes it's better to have textual notation, but sometimes it's also a matter of taste and eventually what the customer wants. And we also discussed, so if we want to create tools that support our language, that also offer the user the possibility to edit models in our language in the concrete syntax that we define, then sometimes this is a very demanding task to do. For example, to develop a graphical PetriNet editor. If you do this by hand, there's a lot of things you would have to implement. Like model view controller code, undo, redo, zoom, error highlighting, validation, properties, windows, and so on. And we said that this is actually something which is also something that model-based software engineering techniques lifted or facilitated and lifted what users have to input, in some cases to the essential minimum that you want to provide. So what you want is just to provide the basic means that the basic concepts that describe your language. And that's typically the definition of the abstract syntax. So the concepts, constructs, and the relationships between the constructs that you have in your modeling language, and some way that you specify how these constructs and relationships in your language should look visually. And I told you about some frameworks that allow you, for example, within Eclipse, there's the editing framework Xerios, which allows you to create or to define based on an eCore meta model for a language, just define the graphical representation of elements, and then it provides you with a graphical editor like you specified it. And there are some frameworks where you have to do some code generation to generate editors, and this is actually a framework which not even requires you to generate code. This is for graphical languages, and then we also looked at a framework for defining textual languages. And the framework we've been looking at is called Xtext, which is an Eclipse EMF-based framework for building textual languages based on an Eclipse modeling framework eCore meta model definition, and it uses a grammar similar to the EBNF form that allows you to describe the textual or the textual mapping, so a mapping from the meta model to the textual syntax in form of a grammar that you can extend or that is extended by constructs for referring to an underlying eCore meta model. And how or what is it that we would like to do? So we could imagine, so this is a running example that I started to explain to you last time, that we want to look at. So let's say we want to define a simple language called entities, where users should be able to define entities similar to classes, or like entities that you know from entity relationship diagrams. And the entity should have attributes like string name and in product number. It should be possible to reference other entities from entities. So we want to say a shop contains a collection of products, for example. And we would like to have some form of inheritance or extension concept. So we would like to say, okay, there are products, for example, there are products in a shop, and a book is a special kind of product. So we essentially, this is a simplified class diagram modeling language, if you want. So we don't want to create editors using a graphical syntax, but we want to create editors that support a textual syntax as shown on the right. So let's start with an example of how such a syntax can be defined. And so this would be sort of the simplest, a very simple Xtext language definition file, where you see a couple of things. And first of all, it's something that just allows you or the grammar just defines a syntax which allows you to define entities. But let's go again through this step by step. So this file consists of, first of all, a grammar namespace or name definition. So we say, okay, grammar and this is the name of the grammar. Usually, you also you give the name in form of or a string that typically you use for namespaces, and then you can import certain grammars, or like you import libraries, and terminals, we will see in a bit, is something that allows you to define that some things in your language are just numbers or names. Now we say generate, and then we give a name here and also a namespace here, or a longer string here. And this says it will generate from the language definition file an eCore model. So there are two possibilities. You can develop a textual representation of an existing eCore meta model, or you can say derive a fitting meta model for the language from this language definition that I'm defining. And this is the latter. So we say generate me an entities model, a model called entities, and this is the namespace URI, which is something that is Eclipse modeling framework specific. So their meta models always have to have a unique a unique namespace URI and SURI, and this will be set. Then we see something here which is model colon and then entities plus equal entity star semicolon. And what is this? This is what's called a rule. So it's a name colon and then something else and then a terminal semicolon. And this is a rule. That's something which is, you could say this is a rule which is applied during the parsing process. And the first rule in such a language definition model is the start rule. It's called a start rule. So this is called a start rule. These rules are something that will be applied on elements that are parsed during the parsing process. And here it says the first element that we suspect to see is a so-called model element. So this is our root element, and what we say is that this consists of a collection of entities. And why is it a collection? A collection it is because we see the plus equal sign, and this means we have a collection of entity elements. And what is the collection of entity elements? This is now something that is provided by 0 or more entities that we will parse with a subsequent rule called entity. So this is also called an assignment. So we assign parsed information, so information parsed by the subsequent rule entity, and we will assign the results to this collection attribute entities. So here you see a bit more information. Some things, sometimes it's things that I also explain, but mainly it's also for your documentation or for your reading, because these are also the slides that I will upload or I have already uploaded. So model is also a type, so it's the type of the root element of our abstract syntax tree. As I said, the model contains a collection entities, and this has, so it's a collection because I have here the plus equal sign, and it's a collection of 0 or many entity elements because here I give the star. The star, as in regular expressions, means 0 or many. Exactly, and this plus equal means we have a collection, and in the underlying eCore meta model, it will be a many-valued e-reference of type entity. So it will be of type entity because here it says entity, and entity is the name of a new rule, which says an entity is everything where I see the keyword entity followed by a name, and the name should be an ID. And we can look at the terminals definition and see that an ID is, and that's what we also interpreted last time. So this means we start with a leading, now I again don't know what this symbol is called in English. Does any? I think we had it last time. Also, does anyone remember what we called it? Not really. Okay, so it starts with this leading roof kind of symbol. This is optional, so the question mark says this may or may not be there. Then next we have something which is as in the next enclosed parentheses, and here it says we can have either a smaller case letter A to Z, or, and this vertical bar is an or a capital letter A to Z, or an underscore, and this can be followed by 0 or many next symbols, which can be either smaller case letters, capital letters, underscores, or digits. Right. So this is the valid format of ID names. So, and once we have this very simple language definition or language grammar file set up, we can generate our editor from it. And this, just to illustrate how this works in Eclipse, is we have here our grammar file. This is something .x text, and there is then also a so-called workflow definition file or workflow file, and this is a file called ending with .mwe2. So this is a workflow engine that can execute a somehow configured workflow, something that then starts code generators and all these kinds of things. And once we run it, it will generate us all kinds of code. For example, it will also generate the ecore file where we said this should be generated. Here you see there is a source gen folder. There will be the code as generated from this ecore meta model, and then we will also have other plugins that then are basically the editors as they then are plugins for Eclipse, and also the parsers, and well, there's also code that then, for example, specifies how certain keywords should be highlighted, syntax highlighting, refactoring operations, and validation code, and so on. And there are also certain points where a user can extend this code with user-specific extensions to the editor. But this is what we will look at a bit later if we have enough time. So, as I said, there is an ecore model being generated, because we say here generate entities with this namespace. And what does this? How does the meta model look for this grammar? And this is now something where we said, okay, we have an abstract syntax tree where the first rule says, okay, I am creating, or whenever I'm parsing a file, I will first of all create an element of this type. So there will be a model which has a collection or many valued reference entities, which will then contain the entities as they are parsed by subsequent applications of an entity rule. So this means we will have one model containing many entities. The entities can have a name. So that's the kind of meta model that we expect. And that's exactly what gets generated if we look at the model, and if we would create a diagram also for it, it would look like this. Model, and then there's a reference, a containment reference actually, to an entity class, and we can have 0 or many entities in the model, and the entity has a name. Exactly what we said, or what I said we expected. So now that's, of course, a very simple language. Now it only allows you to create a model with a list of entities. So how about what do we need in addition here? So what it allows us to write so far is just entity shop, entity product, entity book, entity CD, but now we see more things. We see here, well, every entity has something enclosed in curly brackets. Here, the shop, for example, has a string name and a product, angle brackets product. So intuitively, we want the shop to contain a collection of products. Here we have an integer product number. And what else do we see? We say that entity book extends product. So we have this inheritance extension feature. So how would this be defined in Xtext, in an Xtext grammar? So first of all, let's look at how we extend the entity entry. So the model stays the same. There is nothing besides entities in the model yet. But entities are something more than just a name. For example, we said and this is an optional feature, some entities or entities can but don't have to extend other entities. So now this is something which is optional, and because this is optional, now we have something in braces here with the question mark. So this says, okay, there is something there which is optional. And what is it that is optional? It is something that starts with the keyword extends, and then now we expect some super type to be given here. And now we see we have also again the keyword entity appearing here. So this is a reference to the entity rule. Or I would say that also the entity. So every, let's say every rule that you specify also corresponds to a type or a class in the eCore model. So I would say here by saying super type and then something in these angle brackets refers to another type which occurs, or an element of that type which occurs in your model. So here we say, basically we say we can reference already existing entities. So here we see that this here entity appears in angle brackets, whereas here it doesn't appear in angle brackets. If it doesn't have angle brackets, you say that here you actually expect new entities to occur or to be defined at this point. But if you have here the angle brackets around entity, then you mean to reference an entity that is defined somewhere else. And of course, if entity book extends product, then you don't define the product after the keyword extends, but the product is defined somewhere else. Okay, so this extends construct is optional. And then what does it say? So you expect to see a opening curly bracket, and then a list of attributes. So this here, attributes plus equal attribute star, is very similar to what we had before. So there is a reference attributes of entity, which gets assigned a list of attributes that you parse basically after the opening curly bracket. And then you see here, there should be a closing curly bracket, and the semicolon marks the end of this entity rule. So again, what do we see? We see entity statement or entity keyword followed by a name, an ID, and then this optional extends super type. I explained what these square brackets mean, and then the opening curly bracket, a list of attributes, and a closing curly bracket. Okay. Then it's left to say, so this again is as we have for, so here in this attributes, reference refers to another type, respectively, rule, which we see at the bottom here. It's the attribute rule. And this defines what an attribute looks like. And here we say, okay, an attribute is something that refers to another entity as its type. And now here we see something new. We see something which is, again, a reference of the attribute type. But here we have a question mark equals, which looks very similar to this plus equals, but here it's a question mark equals. And the question mark equals defines that the array attribute, let's say the array feature of attribute is a Boolean attribute. And here the question mark says again, so this combination of an opening and the closing square bracket, if we see it, so this is optional, it need not be there, but if we see it, the array of that respective attribute which we are creating should be true, and if we don't see it, it should remain false. So basically, if we parse an attribute and we see these square brackets, array gets set to true, otherwise to false. Then again, we have a name, and each attribute is followed by a terminal semicolon, and the other semicolon is what marks the end of that rule. And that's basically the bubbles describe what I've been explaining to you. So, if we now say generate here, by what I explained, what do you think the corresponding eCore model should look like? And this is something where I would like you to take 3 minutes to think about it and maybe converse with your partner, and later or after these, or let's say we take 5 minutes, so you think about it, and after we share our results. Okay, so let's say 5 minutes, so the clock here says, well, let's say 5 minutes on that clock, okay? Does anybody have a piece of paper that I could borrow so I can do it for myself too? Or hang on. That's important. Yeah, you have paper. Well, no problem. Yeah, very good. or what I could do, just hang on a sec. So basically the question is, how is this extended into something that reflects all the things that I explained to you before? If you have a question on what things mean here in the grammar, I'm aware that I just explained it and maybe you didn't parse everything I was saying. Just let me know. Okay, any suggestions on how this should be extended? So I don't know, maybe it also helps to show this, I don't know. tell me what's helpful and tell me what you think how this should be extended.
There should be a set relation to entity.
Okay.
So that is extends.
Okay, that's exactly the mistake that I did. I also said extends. But extends, it's what this keyword says. So actually the property type is called super type. Okay? So we can have a super type. And what is the cardinality for this reference?
1.
So 0 to 1 or 1 to 1?
1 to 1.
1 to 1 means each entity must have exactly one super type. So because we have this question.
1 to 0 or 1?
1 to 0 or 1, there is no such thing. So it could be 0 to 1 or 1 to 1. So exactly 1 or no supertype or 1 supertype. So because we have this question mark here, it means it can be said, but that does not need to be.
So 0 to 1.
This is okay. Okay, what else do we have? Containment here. So what are you missing? Shall I re-explain something? You have partial ideas that we can complete together. So now here we said that a model contains entities if we have a construct like this, collection of entities that we parse assigned to an entity's reference, actually containment reference. And so somehow I would suggest that we see the same pattern appearing again. But even if you don't see the pattern, we want to have a language or we want to create a meta model for a language where a model can contain entities and the entity has a type. Okay, we have the type, it can have a supertype. This is what we added now. And an entity can contain attributes, and attributes have an entity type and so on. So what's missing now from our meta model?
Could you explain what array means in attributability?
Yes, sorry. Oops, that's the solution. This is array is just again a name of an attribute So now it gets confusing. We have a class called attribute, and this class has an attribute called array. Okay, and here it means this question mark means it's defined as an e-boolean. This becomes true if we parse the square brackets, and then it's followed by name.
We can have another class called attribute.
Exactly.
Attribute has a reference to entity, or entity has a reference to attribute.
Which one?
I'm not sure, and I mean attribute may have a reference to entity.
Okay, which is because
entity is in angle bracket.
Okay, exactly. So this is similar to the supertype reference of entities to themselves. And the same way an attribute has a reference to entity.
And it has two variables. The first is array, and the type of array is e-boolean.
Yes.
The default value of the array is true. The second variable is name. So the type of the name is string.
Okay. Yes. So what about this reference?
Entity.
It's of type entity, but the name, so do you remember this one was called supertype?
Type.
This one would be type, right? Okay. And the cardinality? So the supertype was 0 to 1 because it was optional.
This is 1.
Exactly. So 1 or let's say 1 to 1 because type is not optional. So there must be a reference to existing entity. Okay, that's it. You think, yeah, that's it. Okay. So what's missing is still, so we said here, the model contains entities, and the same way, entity has a property or a reference called attributes. And this way, an entity contains a list of attributes or a collection of attributes. And so basically this is the same pattern as we see here again. And this reference, this contains is called attributes. And it's because there can be 0 or many, it also has 0 to many cardinality. Okay. So that's exactly what we see here. Okay. Okay. So yeah.
Question. Here, the default value of array is false.
Yes. Well. I'm not sure whether it's important. I think this is just that it's not that we give it an explicit default value, but I think the default value of Boolean is false, and so this is rendered this way in this diagram. Actually, it doesn't matter what the default value is, because the grammar says if we see the square brackets, we will set array to true. And if we don't, well, is it set to false or is it set to the default value, which we have to explicitly say is false? And if we would say it's true, then it would be true no matter what. So whether we see square brackets or not. I'm not really sure about this. Maybe the latter, but this is, again, this diagram or this eCore model is nothing that we specify manually, but it's generated by the tool. So we could have a look at what the actual eCore model says later on, maybe. Okay. So from this, we can now again, let's say we generated the editor from this. If we now start the editor and start editing this an entity model, this is actually what we see. So we have an editor which already highlights keywords that we have in our grammar. So entity or extends were two of these keywords. And we also have a valid, so what else do we have? We have an autocomplete functionality. So this is something which you know from Eclipse or other editors. If you hit, I think it's Control Space in Eclipse, then usually you have some suggestion by the editor of what to type next. And here, the editor is aware that the grammar at this point, if you type extends, that this expects a reference to another entity. And so it will suggest to you entities which you have already specified in the file or in the model, in your entities model. Also, it will tell you, it will show you error markers if there is a syntactical error in your model. So, for example, extends and saying nothing is invalid because it requires to be requires to be followed by a reference to an entity. So what you see here is not a plain text editor like your standard notepad on Windows, but something that has a lot of features: syntax highlighting, error annotations, autocomplete support, also nice default indentation, autocomplete, and also refactoring support. So let's say you have defined an entity product which is extended by book and CD, and you have a shop has an attribute called product. Then, of course, if you want to refactor this model and you want to rename product to item or something else, then what you have to do in order not to break the syntax is to rename all occurrences of product. And that's something that is called refactoring, and that's something what this editor also supports. So in summary, or in partial summary of what this editor is, if you see just a picture of the editor, you would say, oh, okay, amazing textual editor. But just imagine of how much functionality it already packages if you would have to define or program all this functionality by yourself. This would be is already a substantial list of features that would take a lot of time to implement manually. Okay, let's extend the language further, just to get a feeling of some more Xtext features that we can have. So now what our grammar cannot do yet, so we can have references like products, but we cannot express string name or integer product number. And what do we have to do in order to extend our grammar? This is an example. So what do we have now? So we have attributes of entities that can either be typed by existing entities, or they can be typed by other data types. So, for example, string is not an entity, and integer is not an entity, but they represent data types. So just like in Java, you can have a variable typed by a class, or you can have a variable typed by a data type like integer. So here this attribute definition still looks similar to what we had before. So entity is still something that contains a list of attributes. But before we said attribute type, and then we would reference an entity and give a name. Now we say type is an attribute type. And this is something which then is a call to another rule, which then says, okay, the attribute type is something which defines an element type. And then again, what is an element type? And it can be an array or not. So this is also something that we saw before. And now there's also something called length in here. Now, this may be too much of an extension, but did we have this here before? I think not. Okay. So let's say we would also like to include or define the length of an array, and not only whether or not we have an array, but we could also say there could be an optional integer defining the length of an array, and this is what this part then does. The element type now is another rule, and here we say an element type can be either entity type or basic type. And now here we say entity type is then now something that finally is something that refers to an existing entity, or the basic type can be a string, Boolean, or integer keyword. So again, what did we say? We say an attribute is now something that has an attribute type. The type can be an element type or an entity type. An entity type refers to an entity, and a basic type, element type can be entity type or basic type. And the basic type is either a string or is either the string the string int. So let's have a look at what the meta model looks like that gets generated from this grammar definition. Maybe now it becomes a bit clearer of what this grammar is trying to say. So again, we have an attribute. And now instead of saying, hey, this attribute is typed by entity, as we did previously, so you still see the picture here on the blackboard. So this is something what now the entity type does. But what specifies a type is now something which is a separate class. So we have the attribute type. This is something that encodes a length. of an optional array that we can have, and it has one element type, which can be an entity type or basic type. If it's an entity type, we refer to an existing entity. If it's a basic type, then the type name is a string. So if the type name is a string in the meta model, this is a little bit strange, because if you don't see the grammar and you just look at the meta model and you see, okay, I could create a basic type and just type in any type name. So you could also type in Santa Claus, and then this would be your basic type. But this shouldn't be possible. So here it says your basic types are only string, Boolean, or integer. And so this is an example where the meta model generated from your Xtext grammar is more liberal than the grammar definition. So in conjunction with the editor, it will always be used in such a way that we can only define string, Boolean, or integer basic types, because this is defined in the grammar, but the meta model is more liberal. There you could have another approach where you're saying, again, your element type is an entity type or a basic type. Your entity type refers to an entity, and your basic type is of a basic type enum, and here you can define an enum. So basically, this is not an ordinary rule, which would create another class in your meta model, but if you give it the keyword enum here, it will create an enum type, and this would be either string, Boolean, or integer, and this is then the basic type. If it has a kind attribute, then this kind attribute will be typed by the enumeration. So when we look at the corresponding eCore meta model, we will see here now that well, the basic type enum, the kind is of a basic type enum, which contains strings, but the enum defines what kind of, no, I think, no, this is saying that string is sort of the default, and the enum values are here shown as string, Boolean, or int. And this is also something that that Xtext allows you to define. Okay, so this is an example which shows some of the main Xtext features, and this is what I've shown to you, an example where I always showed you what is the generated, or what does the generated meta model look like, which is generated from the grammar. What we can also do in Xtext is we can import an existing eCore model. So let's say we created a meta model before, maybe because your professor told you to do so in your first mini project, or for other reasons. So you have, somebody has an existing language, or they thought of a language first of all on the level of an abstract syntax meta model. They didn't care yet about any kind of textual syntax. So now the task is to create a textual syntax based on an existing eCore meta model. Also, sometimes the question is whether you create your meta model driven by the syntax that you want to create. Then if you really know what your syntax should look like, you can start by the syntax, and maybe you don't care about the underlying meta model, but sometimes it makes also sense to first think about the abstract concepts in your language that you want to have. So you first create a meta model where you say, what are the constructs in my language, their relationships. And when you think you have a nice meta model, you then define a language which fits this meta model. Maybe also you want, you take this approach because you have some constraints on how your meta model should look like, because this is also input to some other type of software, like a transformation, which takes your entities and generates Java code from it. So there are some constraints that from maybe this code generator. So usually if you're serious with language engineering, I would suggest to first start with the meta model. Think of what are the concepts that you really want to reflect in your language, and then think about your concrete syntax, and maybe then make modifications to your meta model so that it accommodates your syntax. But the other way around, first think of a syntax, derive the meta model, and then discover that the meta model is not really very nice. That route is typically more difficult. Okay, so this is, again, let's return to the slide. What we see here is an example of our PetriNet example that we had in this lecture as a running example before. So here is an import statement where we say we import our petrinet.ecore file, and also we have to import ecore. I don't really know why also we have to do this, but that's what we have to do. So we have to import ecore as the ecore meta model, and also our specific model from a file. Okay, so we import this, and remember we have different versions of this PetriNet meta model, but just this is one which we are considering now. This is something where we have a PetriNet that contains a collection of elements. Elements and the PetriNet are named elements, so they can have a name attribute. A net element is either an arc or a node, which can be a place or a transition, and arcs connect nodes. Remember, we again have this issue that we want to disallow connecting places and transitions, but let's be concerned with that later on. So this is now something which we can import. So it means everything we define now in our Xtext grammar has to refer correctly to the existing meta model types and attributes that we have. So otherwise we will get we will have an inconsistent grammar, and we will get error markers. So here we say we again have a start rule, which says, well, whenever you parse something that's a PetriNet, you create a PetriNet instance. So here, actually, when I write Patronet here, this has to be a valid class name here, which is the class Patronet. And again, here we say a Patronet now is something that starts with the keyword Patronet. We have a name for the Patronet, and then in curly brackets, we see a list of net elements. And now we say net elements can be either nodes or arcs, and nodes can be places or transitions, and the place would start with the keyword place and an ID. So what you see here is a pattern here when I can give a type. When I say the type, or I can have a rule which corresponds to a type, and then I say this type can be either one type or another type, then this is something that this corresponds to different subclasses of that type. So net element, the subtypes are node and arc, and we have the same again. The rule node matches nodes, but we have specific rules, place and transition, and so place and transition are subtypes of node in our meta model. Okay. Then, so that's something that we can try. But now it can happen. So these are what follows are some well, maybe rather technical details that I want to explain to you in case you run into them during your mini projects. So there's a mini project, by the way, which I uploaded just this morning, which requires you to create concrete syntax. Well, it requires you to create editors, graphical and textual, for your mini project example language, namely the state machine networks. So you may run into you may attempt doing things like we discuss here in the lecture, and then you also may run into certain problems. The first problem could be that if you have something like this, it says there will be an error marker here, and it says it may consume non-empty input without object instantiation. What? So what does this mean? So that's sort of the error marker that you get. And the technical problem behind it is that here this element list, net element list, may be empty. So it is possible to just have an empty Patronet without anything. So that's allowed by the meta model, and that's actually allowed also by the grammar. And this error occurs because now if this list is empty, the parser will parse the keywords here, and if it doesn't read anything that is a property value that should be assigned to a Patronet, then it won't create the Patronet even. There are some technical reasons why this happens. So the object creation happens when first assignment is executed. So for example, name equals ID. So actually here we had a name, so which is also required. So if we include the name, we won't have the problem. So solution one is add the name assignment, which anyways makes sense for us. Or we say, okay, there must be at least one net element. Maybe we find that empty Patronets are not very interesting or shouldn't be allowed. Or solution three is we specify using this construct that I'm showing here, this is something that says there must be an element created here. Okay. So this is by saying patronage, so the type of element that should be created in curly brackets is the command of creating a patronage whenever I see well, the keyword patronage and the closing, the opening and closing curly brackets, which tell the parser that there is actually a patronage element there. Okay, so that's one issue that you could run into. There are also some more issues. So, for example, remember that we said we must only connect places to transitions and transitions to places. And so this could be a nice idea to encode this in the grammar. To say, okay, if I have an arc, then I must reference a place, then write an arrow, and then reference a transition, or the other way around. So that's a very nice idea. However, you will then see an exception like this. Decision can match input, such as arc, rule ID, arrow, rule ID using multiple alternatives. What does that mean? So when the parser reads tokens representing the source and target nodes, so there will be arc ID, arrow ID, it will see that these are IDs, but it will not know whether it should apply the first alternative of the rule or the second one. It could, of course, look at the ID and try to see is the ID, does it belong to a place or not? But this is at that stage of parsing, it hasn't resolved the types of what the IDs represent yet. So at the point of parsing, it doesn't yet know which of these alternatives to apply. So the grammar is ambiguous at that point, because when the type information is not known, it doesn't know which alternative to apply. And there are again different ways to resolve this ambiguity. Solution one is to add keywords. To say I have something which is either arc, and then I'm saying place to transition by saying PL ID arrow TR ID. So then I know exactly when I parse the string arc and the string PR, I know that I have to apply the first alternative of this rule. And if I see arc and then TR, I know that I have to consider the second alternative. That's something we can do. Or solution two is not to place this alternative, not to define this alternative in our language, in the grammar, which sounded like a nice idea, but it created some problems, obviously. And just say, okay, I just have a source node and a target node. So I'm doing exactly what is allowed by the meta model also. So this is something potentially wrong, but I designed the grammar so that first this is possible. But then I add the OCL constraint to the meta model, as we have also discussed before, which then prohibits connecting places with places and transitions to transitions. And if we do this, So if we take our meta model with the OCL constraints and the language on top, generate the editor and so on, it will actually also invoke the OCL validation in the background. And if there is something wrong with an OCL constraint, this will be also highlighted as an error in our editor. Okay, so that's the second alternative. Now there's actually a third alternative, namely we can implement a custom validation function. So we can have the constraint on the level of the meta model, or we can specify a validation function for the editor, which of course has trade-offs. So if we have this validation function for the editor, it will only be considered by people using the editor, or when by the editor, let's say. But if we have the OCL constraint in the meta model, this is also something that that will be visible, or a concern, or a visible constraint to other tools that are working only on the abstract syntax. So for example, if we have, let's say there is another module which is the an interpreter or code generator for Petrinets. It will open a Petrinet model and then be able to invoke OCL validation and see whether the input it loaded is valid or not. So that's the advantage of having having some kind of well-formless constraints in the meta model. This is something that holds for everybody using it. Whereas a validation function is only sort of a constraint for the editor. Okay, so how can we implement this validation function? Actually, this is something where Xtext generates a lot of code, where we see, if we browse through it, there's actually a package called validation. There is in this case, so assuming that we call the language PNL, so for Petrinet language, there would be a class PNL validator extend. And there is also, there we can add a check method, and this is something which is very close to Java, but has some distinct keywords. So definition of a function is def, and then here this is something that returns actually true or false, but this language doesn't require an explicit return statement. So if we just have an if statement, then this is something which automatically returns true or false. And here we can encode our constraint. And if this is okay, it doesn't return true or false. It says there's an if statement, but so there's actually a void operation. So if this if statement is true, we will raise an error, which is an R can only connect elements of different kinds, basically. Okay, we'll try a few of these things out in the tutorial, provided that time is enough to also get to this validation feature. But I would like to wrap up the Xtext part. So what we have learned, what I have told you today, and you have learned hopefully, is how to define textual language, a textual language with Xtext. We see that we do so with an EBNF style grammar that refers to eCore model elements or will be used to define eCore model elements that can be generated. We saw that this is a framework where by just giving a grammar definition, it generates rich editors with syntax highlighting, refactoring, autocomplete, and so on. And we can easily extend it by validation rules. Also, we can extend it with quick fixes. So, for example, if we, so you know this, for example, from Java, if you type while, and it can suggest to you, okay, you want to create a while loop, so it creates everything that's needed for a while loop. You can manipulate or specify the scoping if you have variables which have where you want to define the visibility. Formatting, so how things are indented and so on, and more. We can import other grammars, so we can combine existing languages or we can modularize our language definitions. And something that Xtext also allows you to do is to create JVM compatible languages. So if you want to create a language that should be executable on the Java virtual machine, there is a way to create your language, your custom language, by defining a grammar by yourself. But then the language concepts that you describe must be mapped to JVM concepts. And so something like a class, an operation, what's a statement, and all these things. So to Java-like concepts, and then you are also able to create JVM compatible, which means languages which are executable on the Java virtual machine, just like Java. For example, this language which you saw, which allows you to define these validation functions. The language is called Xtend, and this is actually a language which was also defined through Xtext, and it's a JVM compatible language which then can be executed on the JVM. So if you ever feel the need to create a JVM compatible language, then this is something you can look into. So what is this good for? So we saw that this is a rich framework where you can build your own domains to textual domain-specific modeling language or modeling languages with quite a minimal effort. These editors are, you can generate Eclipse tools. This grammar is relatively easy to learn. You get a rich editor for free, extensible, but it also has weaknesses. So for example, the underlying parser framework only supports LLK grammars. And if you're familiar with compiler theory, you know that there are also languages which cannot be expressed with this type of grammar. Sometimes also this is a heavy framework, and if you just want to define a simple language where you don't need editor support in Eclipse, then maybe this overhead of tooling that is generated may be too much for you. And one limitation or one constraint is that if you want to create a textual syntax for your meta model, then the meta model and the textual syntax rules, they must not be they must be in some way similar. So every language concept must be somehow reflected in well, so there must be a close relationship between the grammar and the eco model. And if you have a different eco model, then you would probably need to have some kind of a transformation to bridge a substantially different syntax to your model. But this is, yeah, this is sort of not a general weakness of the approach, I would say, but it's just something that you have to be aware of. Okay, so that's it for today. And this is also concluding the concrete syntax chapter. And I will see you in the tutorial and we'll play around with Xtext a little bit. Okay, see you later.